Okay, so this lesson is on observational studies versus experiments. Okay. So just to review, this is just a review of this chapter. We talked about the differences between observational studies and experiments. The goal of observational is to describe some larger group, or to compare groups, or to examine the relationship between two variables. Unfortunately, with the observational studies, again, we cannot prove cause and effect. Confounding. In App 4.1, we talked about teenagers who eat their families 5 times a week, likely to get good grades. Does that mean that that's causing good grades? Unfortunately, it doesn't mean that because there could be other confounding factors. And it wasn't an experiment, right? So we need an experiment to prove cause and effect. So, yeah, some of the confounding variables: do you have a part-time job? How many activities are you in? How many hours do you have available to study? Are you from a wealthy family? There's so many different variables here that could come into play with the differences in your grades. Yeah, exactly. So we wouldn't know for sure which variable was causing the good grades. Is it the eating with your family, or is it one of these other things, right? So we have to design an experiment to test that. The response variable is what we measure. We measure the y variable. We predict it sometimes, but we also measure it. Explanatory variable is what we have control over. Usually, we might have different levels or something, less than 5, more than 5 dinners together, etc. When it's hard to tell or impossible to tell if the explanatory variable is causing a change, we say the two variables are confounded. So even with an experiment, you can have some confounding variables. Confounding occurs when two variables are associated in such a way their effects on a response variable cannot be distinguished from each other. Because of confounding, that's why we can't do correlation. Correlation doesn't prove confounding, doesn't prove causation, because of these darn confounding variables, right? So in a study of more than 4,700 children, researchers from Cincinnati Children's Hospital found that the children whose mothers smoked during pregnancy were twice as likely to develop ADHD. Based on this study, is it reasonable to conclude that a mother's smoking during pregnancy caused an increase in that? Well, was there a treatment here? Did they assign treatments? Did they make the mother smoke or so forth? It's impossible. It is possible the women who smoked had less healthy diets. Yeah, smoking is kind of an unhealthy choice in general, and so you might think, well, maybe those folks don't eat very well, or and that could have caused the problem, poor eating skills. So we don't know what's having the real effect on causing ADHD. Is it poor eating habits, or is it smoking, or many other potential variables there? There were too many potential differences between groups of mothers who smoked. So we want to take away some of those differences. We want to design an experiment in such a way we can handle that. A well-designed experiment is one of the best ways to prevent confounding. So you impose a treatment randomly on some folks, and then the other, other folks get a placebo. We'll get to that in a minute. So treatment is a specific condition applied to individuals' experiment. Lots of times it's a drug. You're trying to lower their cholesterol, so you give them a drug. Experimental unit is the objects or people or animals to which things are randomly assigned. Researchers invited 186 university students to take part in an experiment. While the students were watching a video, they were given brownies to snack on. I like this one. Unknown to the student, the size and number of brownies differed from student to student. There were 3 different sizes: 8, 16, and 32 grams, and 4 different quantities: 1, 2, 4, or 8 brownies. Researchers measured the total weight of brownies consumed. Wow, what if you ate all 8 32-gram brownies? And whether or not each student finished the brownies. List the explanatory variables and the number of possible values for each variable. Oh man, so explanatory variables. So you have control over a couple things, right? The size of the brownie and the quantity of the brownie, right? So the possible number of possible values for each one. So there's 3 for the first variable, the size. There's 4 different numbers of brownies, so 3 and 4. Researchers used every possible combination to form the treatment. How many different treatments were included? It sounds like 3 times 4 would be 12, so probably 12. What are 2 of the treatments? 8 grams, 1 brownie. 16 grams, 4 brownies. Those are 2 possible treatments. There's 10 others. There's 12 treatments. Good. And 3 times 4, that's the counting principle there. And then, again, just list out 2 of the 12 different combinations. What does it learn to be a well-designed experiment? Let's start with a poorly designed experiment. So Mr. Lucko's class wants to investigate if caffeine affects pulse rates. One of the most common studies you can do. If you take psychology in college, you'll probably do this study. One of his students proposed the following plan. Have each student measure his or her initial pulse rate. Give each student 12 ounces of Coke. Wait 15 minutes. Okay? Have each student measure his or her final pulse rate. So it's a pretty easy study to conduct. Compare initial and final pulse rates. So did caffeine make a difference? Can you identify any problems with the proposed experiment? So we waited around for 15 minutes. I don't know how long it takes for caffeine to kick in. I really have no idea. What did you do in that time period, the 15 minutes? Did you sit there? Did you move around? Maybe you were exercising. I don't know. Was it the same kind of cola? Were you sitting down for both cases when you took the pulse rate? I don't know. The cola has sugar as well as caffeine. I didn't even think of that. But sugar could be a confounding variable as well, right? So was it the sugar that made your pulse rate rise or the caffeine? We don't know. Could be other events, right? Such as a fire drill or exciting stats lesson. That would really get your pulse rate up, right? If it's a really fun lesson. Solution for these problems is to have 2 groups in the experiment. One group that receives caffeine and a control group that doesn't receive the caffeine. You've probably heard of this idea of a control group. The reason it's there for comparison. We want to compare the results of the drug or whatever treatment we're giving to a control group that doesn't get the real drug. They get maybe what's called a placebo, like a fake drug, a sugar pill or something that doesn't do much. Sometimes they're given an inactive treatment, again, like a sugar pill, or sometimes a different active treatment. That's occasionally that happens, or no treatment at all also happens. So the 2 groups are treated the same way by the doctors, the people running the study. In fact, oftentimes it's double blind. The people, administering the study don't know if you have the real drug or not. That way, if there is convincing evidence of a difference, it wasn't. We can conclude it was caused by the caffeine. Again, we randomly choose these groups, etc. This means one group we get the regular cola with caffeine. The other group gets the caffeine-free cola. Both groups get the same amount of sugar. I like that. So sugar consumption would no longer be confounded with caffeine intake. Smart. Likewise, both groups would experience the same events during the experiment. So what happens during the experiment won't be confounded with caffeine. So, you want to regulate as much of this stuff as you can so you take out those confounding variables. Use design that compares those 2. So many utility companies have introduced programs to encourage energy conservation among their customers. Electric company, oftentimes they came to my house and told me what to do for free. It's a service they provide. It's kind of cool how you can save money. They considers placing small digital displays in households to show current electricity along with the projected monthly cost. Will the displays reduce electricity use? One cheaper approach is to give customers a chart and information about monitoring electricity use for their outside meter. Would this method work almost as well? It'd be cheaper. The company decides to conduct an experiment to compare the 2 approaches, display and chart, with a control group of customers who receive the information about energy consumption, but no help in monitoring. electricity use. Explain why it's necessary to include the control group. We want it there for comparison, right? We want to see if is it the chart or the electron display, what is it that's actually making the difference? A control group would show how much electricity customers tend to use with no help monitoring the usage. So they're kind of there for comparison. This would be a baseline to determine how much electricity is saved by using the display or chart. Not all experiments require a control group. In the brownie experiment, they don't care if you don't have brownies. They just want to know how much brownies was the best amount to consume, kind of thing. So you don't have to have a control group every single time, although we do a lot, and it's good to have one. Well, not all experiments have a control group. All good experiments involve comparison of 2 or more treatments. Caffeine experiment, we use comparison to help prevent confounding, but even when there's a comparison, confounding is still possible. If each student in the class knows what type of soda he or she is receiving, the expectations of the 2 groups would be different. So we don't want them to know, oh, I'm drinking a regular Coke. That's what the can says, or I'm drinking a caffeine-free Coke, right? So the expectation causes something called the placebo effect, and they actually may get a few degrees better or decrease their cholesterol or whatever it is you're testing. Might have a slight effect from even a fake treatment. It's called the placebo effect. Some is mental, I'm not sure. But describes the fact that some subjects will respond favorably to any treatment, even an inactive treatment. Even a sugar pill that does nothing, sometimes people respond favorably. We're talking about small increases, not big increases here. So other group was a placebo. So by doing that, we're there for comparison purposes. Placebo is a treatment that has no active ingredient, but is otherwise just like the treatment. Again, they look like the real thing. You can't tell when you take them if it's a sugar pill or a regular pill. They're the same color. They look the same. It's just, what it is. A placebo is not that useful if a subject knows he or she is getting a placebo. It is important that the placebo look, feel, and taste just like the other treatments. So they don't know. And lots of times the doctor doesn't need to know, right? It's a double-blind experiment, so the patient and the doctor don't even know. This is what it talks about. So what is double-blind? Double-blind is when neither the subjects nor the experimenter knows what treatment each person is getting. Single-blind, one or the other doesn't know, one does know. Usually the experimenter knows and the person experimenting on doesn't know, the single blind. The electricity example, were the subjects blind? No, they knew what treatment they were assigned to. How do you hide that? You got a digital display or the by hand display. The experiment can still be single blind, however. The person recording the usage doesn't know which household received which treatment. Do placebos work? Wow, this is interesting. One study found that 42% of balding men maintained or increased the amount of hair on their heads when they took a placebo. That is crazy, right? So in another study, researchers zapped the wrist of 24 test subjects with a painful jolt of electricity. Then they rubbed a cream with no active medicine on the subject's wrist and told them the cream would soothe the pain. They were told that, but it was just like cream without any ingredients. When researchers shocked them, again, 8 subjects said they experienced significantly less pain. So just the idea they were getting a cream on their, sore made them feel better. With ailments like depression, some experts think the placebo effect accounts for about 3/4 of the effect of most widely used drugs. Others disagree. In any case, placebo work is a good place to start when you think about planning medical experiments. That's interesting that some people actually think that some of the depression drugs you take aren't that useful, but just the idea that you're taking them make them work. It's interesting. Okay, and go ahead and try this problem on your own. And that's just kind of talking about, just summarizing the lesson that we just did. Okay, that's your lesson for today. Have a good day.